Good afternoon, everyone. My name is Xiaoyong. I'm from Alibaba Pay team. Today, we're going to talk about WHERE, efficient general model training over heterogeneous GPUs. This work represents many work from my colleagues in Alibaba Pay team. To achieve a better model parallelism, the training of large-scale deep learning models has been intensely adopted. The scale of model parameters has increased from millions to trillions. So, however, the scale of model has come at the cost of the engineer effort to efficiently distribute models across GPUs. The commonly used data parallelism strategy is a poor fit, since it requires that model replicas in GPUs thus easily become the bottleneck for the giant models. Meanwhile, training trillions of model parameters requires a terabyte of GPU memory at the minimum, which is far beyond the capacity of a single GPU. However, the scale of model has come at a cost. What? Okay, it's working. So, besides data parallelism, several new parallel strategies for training deep learning workers have been proposed, including pipeline parallelism and tensor model parallelism. Pipeline parallelism splits the input mini batch into multiple micro batches and pipelines the execution of these micro batches across multiple GPUs. Tensor model parallelism splits the operators and the tensor internally over multiple GPUs. In select a proper parallel strategy for model training, both model proportion and computing resource and to be considered. Pure pipeline parallelism does not scale well with more GPUs because of bubbles, resource utilization, and P2P communication. A better approach is to find the proper stage for a model and apply the listed data parallelism for further scaling of the training. In our experiment of very large training, we observed that combined pipeline with 4 stages and data parallelism achieved high speed up than pure, let's say, 8-stage pipeline. Moreover, different parallel strategies can also apply to different model partitions for the hybrid. Here says large-scale image classification models with 100,000 categories. In this model, the fully collect and softmax layers are 10x larger than model size compared to the image feature extraction that backbone. If data parallelism is applied and the whole model the gradient point size of the fully collected will become the bottleneck. One better solution is to apply data parallelism to ResNet 50 and apply model parallelism to fully collected. As a result, the synchronization overhead can be reduced by 90%, thereby achieving better performance. Training of giant model requires huge computing resources. In industry, the scheduling of 100 homogeneous high-end GPUs usually requires long queuing time due to the Gang schedule. In such a scenario, heterogeneous GPUs can be obtained much easier as a computing pool. For example, a pool of P100, B100, A100, this kind of mixer pool. However, deep learning frameworks encounter challenges in efficient utilization heterogeneous resources. Different types of GPUs are, different types of GPU memory capacity and GPU computing capacity, which relatively introduce imbalance in computation graph partition and deep learning operator allocation. We summarize the gap in giant model training using existing approaches. Firstly, the framework lacks a unified abstraction to support all of the parallel strategies and the hybrids. Secondly, for the automatic parallel strategies, searching is time-consuming for giant models. The third is inefficient when training with heterogeneous GPUs. Model developers can hardly consider all resources issued when programming. Finally, current approach couples model code to the specific model parallel strategies, which requires significant code refactoring when applying the strategy to a new model or switch between the parallel strategies. These gaps also bring the opportunities to build better training frameworks for giant models with multiple parallel capacity. We start with defining a unified programming language for strategy expression. After that, the framework is enhanced to utilize the hints with the best possible resource utilization. Due to the heterogeneous GPU, parallel strategies should be used adaptively and dynamically. Finally, user can implement parallel strategies with minimal code change and switch among strategies easily. We propose WHERE, a deep learning framework designed for training giant models with high performance for carefully balancing user effort and distributed graph optimization requirement. We introduced 2 new high-level primitives to express all existing parallel strategies as well as their hybrids. By utilizing the annotation for graph optimization, we can transform local models into distributed models and train them on multiple GPUs efficiently and automatically. We propose a hardware-aware load balancing algorithm, which is seamlessly integrated with the parallel strategies to accelerate training on heterogeneous GPUs. We will demonstrate its capacity by setting a new milestone in training the largest multimodality pre-trained model M6 with 10 trillion model parameters. To elaborate well, I will start with the key abstraction and parallel primitives. Then I will describe a parallel planner that transforms a local model with the parallel primitives into a distributed model. Finally, I will introduce a hardware-aware load balance algorithm to speed up the training with the heterogeneous GPU clusters. Let me introduce 2 internal concepts here, that's task graph and a virtual device. Task graphs is a subset of the model for parallel transformation and execution. One model can have 1 or more non-overlapping task graphs. We can apply parallel strategies to each task graph. By modularizing model operations into task graphs, we can apply different strategies to different model parts, as well as scheduling the execution of task graphs in a pipeline. A task graph can be further replicated or partitioned. Virtual device is a logical representation of the computing resource. With one virtual device have 1 or more physical devices. Virtual device hides the complexity of, device topology, computing capacity, as well as device placement from the user. One virtual device is assigned to one task graph. Different virtual devices are allowed to have different or the same physical devices. The parallel primitive is a the Python context manager, where operations defined under it are modularized as one task graph, where allows users to suggest parallel strategies with 2 unified primitives, replicate and split. Replicate allocate a task graph to be replicated. Device count is the number of devices used to compute a task graph replicas. Split allocate the task graph to apply intra-tensor sharding. The device count here denotes the number of partitions to be sharded. Each sharded partition is placed on one device. To implement this, the auto-parallel mechanism is encoded to simplify the user experience. The first example here shows a pipeline parallelism with 2 task graphs, which with each task graph, they have configured with 1 device. The pipeline parallelism is enhanced by configuring pipeline non-micro batches. The total device number of the 2 task graphs is summed to 2 if the available device necessary number is 8, which is 4 times of the total device number, where we apply 4-degree data parallelism beyond the pipeline. The second example shows a hybrid strategies that replicate the ResNet 50 features part with splitting the classification model part. The parallel planner is responsible for producing an efficient parallel execution plan, which is the core of the WHERE runtime. The parallel planner takes a local model with optional user annotation, computing resource, and optional configures as input. The virtual devices are generated given computing resources and optional annotation automatically. After that, the model is partitioned into task graphs, and the task graph is further partitioned internally if split is, let's say, annotated. Since we are applying different strategies to different task graphs, there may exist input-output mismatch task graph. So in such a case, the planner will try to insert the corresponding bridge layers automatically between the two task graphs. Here, the bridge layer is gather the distributed tensors and then feed them into next task graph. Here we describe how we utilize the hardware to balance the workload among task graphs, which achieved high performance even in heterogeneous GPU clusters. In general, we'll try to balance the computing pool proportional to the device computing capacity subject to the memory constraint. For data parallelism, we balance the flops, adjust the local batches with keeping the mini batch unchanged. For tensor model parallelism, we balance the flops or partitional operations through uneven sharding. The memory constraint algorithm can be achieved by, let's say, sorting and reordering the device in corresponding virtual device by memory capacity from higher to low. It's a greedy plan algorithm consider local range, load ratios, basically, memory and flop utilization. There might be a case where later stage contains large layers, for example, large sparse embedding, which can be addressed in the algorithm or handling out of memory errors. Where multiple task graphs are executed in the pipeline, which balance the inter-task graph workload or heterogeneous GPUs. Pipeline parallelism achieves efficient execution by interleave forward-backward execution among multiple micro batches. Only a task graph leads to cache more activations than later task graphs. Thus, only a task graph usually consumes more GPUs memory than later task graphs. This is shown in the right finger. The different memory requirement of task graphs motivate us to place earlier task graphs on device with high memory capacity. After reordering the virtual device according to the memory requirement, we partition the model operations to task graphs in a topological sort, and then balance the computation flops among operations proportional to device capacity, subject to the memory bound of the memory capacity of each device. We will show you some evaluation result and conclude our work. So basically, we first demonstrated that where is the efficient single parallel strategies by comparing with TensorFlow asymmetric DP and G-pipe pipelines. We evaluate where DP by competing with the TensorFlow asymmetric DP using the Bertrand large and the ResNet 50. Here, where DP consistently obtained better speed up and higher GPU utilization than TensorFlow asymmetric DP. Such things could be attributed to Where's computation optimization technologies, such as hierarchy or grouped or reduced. We then evaluate the efficiency of Where pipeline parallelism by comparing with the G-pipe. As shown in the right finger, the training throughput speed up Where out from G-pipe in both 4-stage and 8-stage by 1.45x and 1.14x respectively. We attribute the performance gain to the use of alternating forward-backward schedule policy, which improves GPU utilization. We then invented hybrid strategies. We first apply a nested pipeline with DP to the Bertrand large models with V100 GPUs. The model is partitioned into 2, 4, and 8 number of task graphs. The left finger shows that pipelines with 2 task graphs and 4 task graphs get a similar training speed up on GPU utilization. However, we observed a performance drop on 8 task graphs at a lower GPU utilization compared to 2 and 4 task graphs. This is because 8 task graphs node to be a relatively lower module operations in each task graph, and the GPU utilization computation is not enough to overlap the inter-task graph communication, resulting in poor performance. Next, we evaluate the combination of hybrid strategies on a large-scale image classification model. We perform experiment on classification number 100,000 and 1 million on different number of V100 GPUs. To reduce the communication overhead of a hybrid parallelism, we mix the ResNet 50 replicate with the 40 collected partition. We compare the hybrid result of 100,000 classes with the data parallelism. As shown in the middle figure, hybrid parallelism outperforms the data parallelism by 1.2 for 8 GPUs, 1.7x for 16 GPUs, and 2.4x for 32 GPUs for training throughput speed up. With the number of workers increase, hybrid parallelism maintains a near linear kind of speed up, while the DP strategies fall dramatically beyond the 8, I think 6 workers. This is because the heavy 40 collector layer incurs a huge gradient synchronization overhead. For the task of 1 million classes, data parallelism failed due to out of memory. With hybrid parallelism, where allows for the training of image classification task with 1 million classes. The right finger shows that the performance of hybrid parallelism. The training throughput from 8 GPUs to 32 GPUs achieved a 95% scaling efficiency. In terms of hardware-aware load balancing result, for data parallelism, we evaluate 3 typical models, including ResNet 50, Bernard, and GAMT. The experiments are conducted on heterogeneous GPUs that consist of 8 32 gig V100 and 8 16 gig P100. We set the same batch size for all models as the baseline. We then apply the hardware-aware algorithm to each model and get the speedup compared with the baseline performance. We outperform the baseline in all 3 models by a factor of 1.3x and to 1.4x. For pipeline parallelism, we evaluated 2 models, including Bird large and the T5 large. The training is the performance on heterogeneous GPUs that consist of 4 32 gig V100 and 4 16 gig P100. Both Bird large and T5 large are partitioned into 4 stages. We first apply a listed data parallelism to pipeline. We set the evenly partitioned models as the baseline. We conduct the training with the hardware-aware policies and then get about 20% speed up on both models. Finally, we use WHIR to train the industry-scale giant models, M6, the Chinese multimodality model. We parallelize the training of M6 10 billion models with a hybrid parallelism strategies by listing the pipeline parallelism and the data parallelism. When scanning the computing nodes from 8 to 256, WHIR achieved 91% sustainable. WHIR can easily scale to a local M6 models to a distributed one by only adding a few lines on top of the module definition as shown in the top left figure. In bottom figure, WHIR scales the most parameter to 1 trillion by switching the hybrid of data parallelism and the tensor model parallelism with only a small number of lines of code change. At the end, WHIR train 10 trillion parameters by adopting optimized tensor offloading strategies with 512 NVIDIA V100 GPUs. In conclusion, we present WHIR demonstrated the possibility of achieving efficiency, programmability, and adaptability in a scalable deep learning training framework for training trillion parameter models. WHIR supports various parallel strategies using a unified abstraction. It hides the distributed execution details through new pipeline annotation and adapts to heterogeneous GPUs with automatic graph optimization. The code of where is now open source in GitHub. You can also try it out on PayDLC, a cloud-native deep learning training partition on Alibaba Cloud. So, okay, that's all for my talk. Thanks for your time. Any questions?